Today we're going to walk through a construction that derives the standard model gauge groups, three fermion generations, a geometric Higgs sector, and a decoupled dark matter candidate, all from a single algebraic object living in the complex Clifford algebra CL6 of C. The Standard Model is arguably the most successful physical theory ever constructed. Its predictions have been confirmed from sub-eV neutrino oscillations to TV scale collider physics. And yet it's structurally incomplete in several striking ways. First, it offers no explanation for why there are exactly three near-identical fermion generations. Second, roughly 85% of the cosmic matter budget is dark matter, something the Standard Model doesn't contain. Third, the weak interaction violates parity, but this chirality is imposed by hand, not derived. And finally, the gauge group SU 3 times SU 2 times U1 is assumed, not explained. What if none of these are fundamental inputs? What if they're all emergent features of a deeper, more economical geometry? The construction starts with the complex Clifford algebra CL6 of C, generated by three pairs of fermionic ladder operators, alpha hat sub A and alpha hat dagger sub A, for a running from 1 to 3. These satisfy the canonical anti-commutation relations with a Hermitian fiber metric. Critically, this is a metric on the internal fiber space, not on spacetime. As a complex algebra, CL6 of C is isomorphic to 8 by 8 complex matrices, 64 complex dimensions. That's precisely enough for one complete standard model generation together with its dark sector mirror copy. The picture is a fiber bundle. At each point of four-dimensional spacetime, we attach a copy of this Clifford fiber. The spacetime gamma matrices aren't put in by hand. They're constructed from real linear combinations of the fiber ladder operators. To organize the algebra into particle states, we introduce idempotent projectors. From each ladder pair, we build JA plus and JA minus. Since the three J operators commute, their products give us 2 cubed, 8 mutually orthogonal left ideals. These 8 columns of the matrix algebra correspond to physical particles. The 4 light ideals contain the neutrino, electron, and quarks. The 4 dark ideals contain their mirror counterparts. The split is governed by the fiber pseudoscalar I equals J1, J2, J3. The projectors P plus and P minus select the 2 eigenspaces. This decomposition is exact. P plus times P minus equals 0. No mixed Feynman diagrams. The only coupling between light and dark is gravitational. Rather than postulating gauge groups, the paper derives them from a single physical requirement. The Dirac probability current J mu must transform as a proper spacetime vector. Under a general transformation, E psi maps to L psi u, where L acts from the left and U acts from the right. For the current to remain a Lorentz 4 vector, 2 conditions must hold. First, the right action U must be unitary. This is automatically satisfied by all rotors in U3, no constraint at all. Second, the left action L must map the spacetime bivectors gamma 0, gamma mu into Lorentz rotated versions of themselves. This second condition is where the magic happens. Here's the crucial step. The spacetime gamma matrices are not primitive objects. They're constructed from specific combinations of the fiber ladder operators. Look at the explicit formulas. Gamma 0 involves alpha hat 1 and alpha hat 2. Gamma 1 involves alpha hat 2 and A13. Gamma 2 is built from alpha hat 2 alone, and gamma 3 uses alpha hat 1 and alpha hat 2. Notice a pattern? Now look at the spacetime bivectors, the objects gamma 0, gamma mu that appear inside the current J mu. Gamma 0, gamma 1 involves alpha hat 1, alpha hat 1 dagger, and A23. Gamma 0, gamma 2 involves only alpha hat 1 and alpha hat 1 dagger. And gamma 0, gamma 3 is simply J1. The critical observation is that all of these bivectors are built from just alpha hat 1 dagger, J2, and J3. They live entirely within the first fiber plane and the diagonal observables of the other 2 planes. Visualize the 3 complex fiber planes. The spacetime gamma matrices have chosen plane 1 as their home. The spacetime embedding lies primarily in the alpha hat 1 direction. This choice breaks the symmetry among the three planes. It distinguishes plane 1 from planes 2 and 3. Now here's the key constraint. The left action L must map the spacetime bivectors to Lorentz-rotated versions of themselves. Since those bivectors are anchored in the alpha hat one direction, L cannot rotate plane 1 into planes 2 or 3. That would scramble the spacetime embedding, and the current would no longer transform as a vector. So what can the left action do internally? It can only rotate within the alpha hat 2, alpha hat 3 subspace, planes 2 and 3. The group of unitary rotations in a two-complex dimensional space is U2. This is precisely SU2L times U1L, the electroweak gauge group. It emerges not as an assumption, but because the spacetime embedding has frozen out one of the three fiber directions for the left action. So the full U3 of possible left fiber rotations is reduced to U2, exactly the electroweak group, by the single requirement that the probability current transforms as a spacetime vector. Why doesn't the same constraint apply to the right action? Look at how U enters the current. It appears as U dagger times something times U, a conjugation acting on the entire bracketed expression. As long as U is unitary, meaning U dagger U equals 1, this conjugation cannot change the scalar part of the current. U never directly touches the spacetime bivectors. It acts on a different side of psi altogether. So the right action retains the full U3 symmetry of the fiber. This decomposes naturally into SU3 color, which rotates the three quark color ideals, and a commuting U1R phase rotation. The right action is blind to chirality. It treats left-handed and right-handed states identically, exactly as the strong force does. Let's summarize the asymmetry. The left action must preserve the spacetime bivectors which live in plane 1. This freezes one direction out of 3, reducing U3 to U2, the electroweak group. The right action only needs unitarity. It never touches the bivectors, so all three planes remain free, giving the full U3, color plus hypercharge. This single geometric distinction between left and right is why the weak force is chiral, while the strong force is not. The weak force is chiral because the spacetime embedding selected a preferred fiber direction, and it's the left action, not the right, that must respect that selection. No separate parity violation postulate is needed. It's a geometric consequence of where spacetime sits inside the Clifford fiber. The three complex fiber planes can be cyclically permuted without changing the defining relations. This slide automorphism S satisfies S cubed equals the identity, producing three inequivalent spacetime embeddings, identified with the three Fermion generations. All three generations see the same gauge fields. What differs is which fiber plane sources the Higgs coupling, setting the Yukawa masses. In this construction, the Higgs isn't an independent field. The pullback field F maps space-time into the complex fiber, inducing a Hermitian metric with 12 real degrees of freedom, matching the Dirac mass parameters exactly. The electroweak Higgs lives in the 3 block of the induced metric. The potential emerges from the induced internal volume functional, minus mu squared h squared plus lambda h to the fourth. Symmetry breaking is a geometric instability of the trivial embedding. The dark sector inherits the same gauge symmetries, but with conjugated charges. The two sectors decouple exactly. P light times P dark equals 0, meaning no mixed Feynman diagrams. Charges are mirror flipped and masses are inverted. The dark proton is heavier than the dark neutron, making dark protons unstable, while dark neutrons are stable, the exact opposite of our world. Because the dark proton is heavier, it decays via beta-type processes into a dark neutron, a heavy dark neutrino, and a light dark positron. The dark relic is dominated by neutral particles, dark neutrons, and heavy dark neutrinos. They can't radiate electromagnetically, so structure formation proceeds only through gravity. This is exactly the behavior we observe for dark matter. The full action combines Einstein gravity with a higher curvature correction, the fermion kinetic term, standard Yang-Mills field energies, and the geometric Higgs-Yukawa sector. The couplings unify at roughly 10 to the 16 GeV, predicting sin squared theta W equals 3/8. Standard renormalization group running reproduces the observed electroweak mixing angle. No new gauge fields needed. To summarize, The standard model gauge groups, chiral-weak interactions, 3 generations, the Higgs mechanism, an exactly decoupled dark sector, dark matter as neutral relics, and gauge coupling unification, all from a single algebraic choice. Open questions remain: the Yukawa hierarchy, mixing matrices, neutrino masses, the dark to visible abundance ratio, and quantizing the pullback field. The central message is clear: a remarkably large fraction of the standard model and a compelling dark matter candidate follow from one algebraic choice, a superspinor in the complex Clifford fiber over spacetime. Thank you for watching.